40 million people right now, and most of them have no idea what is heading their way. Not a metaphor, not a number inflated for clicks. 40 million is the real figure that forecasters at the Storm Prediction Center in Norman, Oklahoma, placed inside an active warning polygon in the final days of April 2026. A corridor stretching from northern Oklahoma up through southern Minnesota. 800 miles of alert boxes stacked like dominoes on a map that meteorologists had already redrawn 3 times in a single week. 3 rewrites. That is not normal. When the people whose entire career is reading the atmosphere keep changing their forecast, it means the atmosphere is doing something they did not expect. And what it was doing in those final hours before the storms fired was building energy at a rate that the models had consistently underestimated since the beginning of the season. The Storm Prediction Center is not a dramatic institution. They are deliberately restrained. Their language is calibrated, careful, almost clinical. When they raise a risk level, insurance companies move. Emergency managers call in overnight staff. Pilots reroute entire flight plans. Airlines cancel departures from cities that aren't even in the direct path yet. So when that office began using the phrase enhanced risk for the corridor sitting between Oklahoma City and Minneapolis, and then upgraded it again, and then again, the people watching those words understood something that the general public had not yet registered. This was not a routine spring storm. This was a pattern that had been loading the same corridor for weeks, firing the same geography again and again, and the 40 million people sitting inside that polygon were about to experience the next pulse of something that had already broken records no one wanted broken. To understand why this storm was so severely underestimated, you have to go back further than the week it happened. You have to go back to the beginning of the 2026 severe weather season and look at a number that almost nobody outside of meteorology was paying attention to. By mid-April of 2026, the National Weather Service office in Chicago had already issued 128 severe thunderstorm and tornado warnings for the year through that date. That is a record for that office, not a near record, not a historically elevated number, a record. And the season was still adding to it every single day. The average severe weather season in the United States climbs through March, peaks somewhere in mid to late May, and then gradually tapers as summer heat stabilizes the atmosphere. Early April is usually a transition period. Warm air is still fighting winter cold for dominance. Outbreaks happen, but they tend to be scattered, local, manageable. The big multi-state events, the ones that reshape towns and fill FEMA databases, are usually still a few weeks out. 2026 did not follow that timeline. The season broke early, and it broke hard. On April 17th alone, a single outbreak across the central United States produced 46 tornadoes in one continuous event. 46 in one day. A high-end EF2 tornado tore through the southern edge of Rochester, Minnesota. Another high-end EF2 shredded the town of Lena, Illinois so thoroughly that the Stevenson County Sheriff's Office asked the entire public to stay away from the town entirely. That request is almost never issued. Emergency services typically open roads as fast as possible. A full public avoidance order means the damage was so total, the power infrastructure so compromised, the gas lines so uncertain, that even curious drivers represented a danger to themselves. Aerial footage taken in the hours after the tornado passed showed a continuous track of destruction several hundred yards wide, cutting through the town like a blade drawn by an invisible hand. And that was before the storm that was now heading toward 40 million people had even begun to organize. The ingredient that most people never think about when they picture a tornado is not the wind. It is not even the rotation. It is the moisture. Specifically, it is where that moisture comes from and how warm it is when it gets there. The Gulf of Mexico sits directly south of the American severe weather corridor, and its surface waters have been running measurably warmer than historical averages for several seasons now. Warmer water evaporates more efficiently. More evaporation means more water vapor in the air column above it. More water vapor means higher dew points, reaching further inland than they used to. And higher dew points reaching further inland means the severe weather corridor extends further north than the old maps show. On the day the 40 million person warning was issued, meteorologists were tracking mid-60s dew points pushing well into Minnesota. Mid-60s dew points in Minnesota in late April. That is Gulf of Mexico moisture reaching the Canadian border. That is air that belongs in Louisiana sitting over the northern plains. And when that warm, saturated air collides with the cold continental air still pouring down from Canada, the atmosphere does not blend them gently. It tries to mix them violently. That violence has a name in meteorology. It is called a severe thunderstorm. But the storm that was forming on the western edge of the corridor was not just a severe thunderstorm. It was something more organised, more dangerous, more patient. The atmosphere above the Central Plains had spent days building a configuration that experienced forecasters recognise immediately when they see it on the models. A deep trough in the jet stream anchored over the western United States, a strong surface low developing across the Central Plains, a sharp dry line sliding east across Texas and Oklahoma, dragging the boundary between desert air and Gulf air forward like a curtain being pulled across a stage. And behind that curtain, a warm sector loaded with the kind of instability that forecasters measure in a unit called CAPE. Convective Available Potential Energy. The number is how much fuel the atmosphere has loaded into the column above a specific location. Think of it as the length of the runway a storm has to accelerate before it hits something that stops it. The longer the runway, the faster the storm goes. The forecast was calling for CAPE values between 2,000 and 3,000 joules per kilogram across the warning corridor. 2 to 3,000. For context, 500 is considered weak, 1,000 is moderate. Values above 4,000 have been recorded during some of the most catastrophic tornado outbreaks in American history. 2 to 3,000 is high. Not historic, not record, but more than enough. More than enough to take a thunderstorm that fires along the dry line in the early afternoon and turn it into a rotating supercell before sunset. The dry line itself is worth understanding because most people have never heard of it, and yet it is one of the most reliable storm factories on the planet. Somewhere across West Texas and the Oklahoma Panhandle, an invisible boundary slides east every spring afternoon. West of that line, the air is hot and dry, pouring off the high deserts of New Mexico and Arizona. East of it, the air is warm and saturated, pulled north out of the Gulf. The two air masses do not mix. They collide, and where moist air gets lifted suddenly past its dew point, thunderstorms ignite. Storm chasers know the dry line the way surgeons know a scalpel. They position themselves on its eastern edge in the late afternoon and watch a completely clear sky. Then a small puff of cumulus appears. Within 30 minutes it is a tower. Within an hour it can be a supercell with a rotating wall cloud that reaches from the storm base to within a few hundred feet of the ground. The dry line does not announce itself with drama. It simply delivers. In 2026, forecasters have been noting all season that the dry line was sharper than usual. The contrast between the dry air and the Gulf air was stronger than typical springs. That sharpness meant storms were firing more efficiently, more discreetly, more dangerously than a blurry boundary would produce. Wind shear is the other ingredient that most people hear about, but almost nobody truly understands. Picture a hot dog held horizontally between your palms. Push your right hand forward and your left hand backward, and the hot dog rolls. That invisible rolling is happening in the atmosphere at every altitude above a storm simultaneously. Wind near the ground might be moving south to north. Wind 3,000 feet up might be moving southwest to northeast. Wind at 30,000 feet might be screaming west to east. Different directions, different speeds, stacked in layers, the atmosphere rolls along invisible horizontal tubes. Normally those tubes stay horizontal and harmless, but when a thunderstorm fires and begins pulling warm, moist air upward at its base with enough force, it can tilt one of those horizontal rolling tubes vertical. Suddenly, what was a harmless, invisible spin becomes a vertical column of rotation inside the storm. Meteorologists call this a mesocyclone. It is typically several miles wide. It is usually invisible unless you are watching the entire storm from a distance and can see the whole thunderhead rotating like a slow top. The mesocyclone is not yet a tornado, it is the cradle. Inside that rotation, smaller, tighter vortices can develop, condensing like a figure skater pulling their arms in during a spin, concentrating the rotation into a narrower and narrower column until it reaches the ground and connects cloud base to surface, and at that moment, the tornado exists. The forecast for the corridor on that day was showing effective wind shear values around 40 knots through the depth of the storm. 40 knots. That is roughly 46 miles per hour of directional change between the lowest and highest layers of the atmosphere. That is solidly in the range where supercell thunderstorms form, where long-track tornadoes become possible, where the kind of event that reshapes a town rather than just damages it starts to look like a realistic outcome. It is not the most extreme shear value meteorologists encounter, but it is the number that makes them start adding specific tornado language to their outlooks. And it was sitting directly over a corridor containing 40 million people who had been told the storm was coming, but had not been told just how ready the atmosphere was to produce the worst of what it could offer. Here is the part of the story that almost never makes the broadcast. The scale that forecasters use to communicate risk to the public sounds gentle. It is not gentle. Level 1 is called marginal, Level 2 is called slight, Level 3 is enhanced, Level 4 is moderate, Level 5 is high. Those words sound like they climb gradually, like a staircase with shallow steps. They do not climb gradually. The jump between each level is closer to exponential than linear. A slight risk, the word that sounds almost like a shrug, statistically covers the zone where the majority of American tornadoes actually occur in any given year, because slight risk areas are enormous. They cover vast stretches of land where people live, sleep, drive, work. A high risk is something forecasters issue only a handful of times in any given year. When they do, hospitals begin pre-staging ambulances before the storms even fire. The word slight has killed people. Not because the forecast was wrong, because people heard the word slight and went to bed. The storm that destroyed Lena, Illinois earlier that month started inside a risk zone that was not at the top of the scale. The tornado that killed people in Michigan earlier in 2026 developed inside a marginal risk, Level 1. No tornado watch was ever issued before it struck. The words on the map are calibrated for the atmosphere. They are not calibrated for human psychology. And the gap between those two things is where fatalities happen, again and again, in the same kinds of places, to the same kinds of people, making the same kinds of decisions. Illinois is a state that most Americans do not think of as severe weather country. Oklahoma, Kansas, Texas, those are the names people associate with tornadoes. The image burned into public memory is flat land, open sky, a funnel visible from miles away, giving you time to think and move and prepare. Illinois is not that. Illinois is flat in many places, but it is also densely populated, dotted with small towns that are difficult to warn in time, and sitting in a landscape that has no protective terrain to slow or weaken an approaching storm. And in 2026, Illinois was leading the entire United States in tornado reports, hail reports, and damaging wind reports simultaneously. Through April 19th, Illinois had logged 80 confirmed tornado reports. The second-place state, Mississippi, had 43, almost double. 147 hail reports, 245 damaging wind reports. Leading in all three categories at the same time is almost unheard of for a state that was never supposed to be the centre of the map. The reason Illinois finds itself at the top of those rankings connects directly to something researchers have been tracking for roughly 2 decades: a slow, steady, measurable eastward shift in the centre of American tornado activity. Tornado Alley, the corridor that defined severe weather geography for most of the 20th century, ran through the southern plains. Oklahoma, Kansas, Nebraska, the Texas Panhandle. Those states dominated the rankings for generations. A secondary zone called Dixie Alley ran through Mississippi, Alabama, and parts of Tennessee with its own deadly character. Illinois was never the headline state. It got hit, yes, but it was never the leader. The map has rearranged itself. Scientists have proposed several mechanisms. The jet stream has been digging its trough further west in recent springs, which pushes the main storm track further east at the surface. Gulf moisture has been penetrating further north and east as sea surface temperatures rise. Cold fronts rolling out of the Rockies have been firing their severe weather slightly later than historical averages, meaning storms reach their peak intensity right as they cross into Illinois and Indiana, rather than earlier over Kansas. The state is catching storms that have had time to mature. A supercell that fires in western Kansas at 2 in the afternoon needs several hours to reach full strength. By the time it crosses into Illinois that evening, it is often at its most dangerous. And Illinois has no terrain to slow it down. The April 17th outbreak put this on full display. 27 confirmed tornadoes touched down in Illinois during that single event. More than half of all tornadoes from an outbreak that spanned from Oklahoma to Wisconsin landed on Illinois soil. The town of Lena in Stevenson County took a direct hit from a high-end EF2 with winds between 125 and 135 miles per hour. Winds that fast can strip a roof off a house in under 3 seconds. They can lift a vehicle off the ground. They can turn a piece of broken glass into a projectile that travels faster than a car on a highway. The Lena damage track was continuous, several hundred yards wide, cutting through the town for a distance that left aerial survey teams labeling it remarkable. That word, remarkable, used by the Chicago Forecast Office in their official public summary, is restrained language from people who spend their careers being restrained. When forecasters call something remarkable, you pay attention. And now, weeks later, the same corridor was loading again. The same jet stream configuration. The same Gulf moisture surging north. The same dry line sharpening across the Oklahoma panhandle. 40 million people sitting inside a polygon that forecasters had redrawn 3 times. And the question hanging over every radar screen in every National Weather Service office from Tulsa to Minneapolis was not whether storms would fire. The atmosphere had already answered that. The question was, what kind of storms would fire first, and how long the most dangerous window would last before the individual supercells merged into something different, something that trades one kind of danger for another. Supercells and squall lines are not the same animal. A supercell is a single isolated rotating thunderstorm. It stands alone on the radar, sharp-edged, persistent, pulling in its own fuel, organising its own rotation over hours. It is the storm type responsible for most of the long-track, violent tornadoes in American history. A squall line is a wall of storms stretched across hundreds of miles, moving together as a single, organised front. Inside that wall, winds can accelerate into devastating straight-line bursts. Brief spin-up tornadoes can drop and lift along the leading edge, touching down and disappearing before a warning can even be issued. The squall line loses some of the rotation that makes supercells so dangerous for long-track tornadoes, but it gains something else. A bowing squall line can pack its outflow into a concentrated wall of wind, racing east at 60, 70, sometimes 80 miles per hour, flattening trees and downing power lines across a path that can span multiple states in a single night. The forecast for that day described exactly this sequence. Storms expected to develop as discrete supercells in the late afternoon along the dry line and warm front, then grow upscale into bowing segments overnight, moving east-southeast into a strong, low-level jet. That last phrase, into a strong, low-level jet. It sounds technical. What it means in plain language is that the squall line forming after dark would be fed by a ribbon of fast wind close to the ground that strengthens after sunset, pumping energy into the storm system through the night, keeping it alive and dangerous well after midnight, well after the people inside the warning polygon had gone to sleep. The nighttime tornado problem is a completely separate category of danger from everything that happens in daylight. Research on tornado fatalities has shown for decades that nighttime tornadoes kill at rates roughly twice those of daytime tornadoes of comparable intensity. The reasons are not mysterious. People are asleep. Phones are silenced. Sirens outside a closed bedroom window in a house with central air conditioning running do not penetrate the way a conversation does. And mobile homes, which represent a significant fraction of housing across the rural South and Midwest, offer almost no structural protection against tornado-strength winds, regardless of what time the storm arrives. A weak tornado, an EF0 or EF1, can roll a mobile home off its foundation. A moderate tornado destroys one completely. A strong tornado reduces one to debris scattered across multiple counties. The occupants inside, no matter how prepared, have almost no chance of surviving in place if the structure takes a direct hit. The only safe option for a mobile home resident when a tornado warning is issued is to leave before the storm arrives. Every safety briefing produced by the National Weather Service in recent years has said exactly this. Leave. Go to a neighbour's basement. Go to a community storm shelter. Go to any nearby permanent structure. Do not stay. The advice is clear. The execution is brutal. Many mobile home residents have limited transportation. Many live in rural areas where the nearest permanent structure is miles away. Many receive the warning while asleep, too late to drive anywhere safely in the dark, with a storm already on radar approaching at 50 miles per hour. The specific type of tornado most likely to occur in the overnight squall line phase has a technical name that almost nobody uses in casual conversation. Forecasters call it a QLCS tornado, quasi-linear convective system tornado. A tornado that spins up inside the leading edge of a squall line, where a bulge in the wind structure creates brief, tight rotation. These tornadoes form fast and die fast, and the warning lead time is often measured in seconds rather than minutes. A supercell tornado develops from a mesocyclone that can be tracked on radar for 20 or 30 minutes before it touches the ground. A QLCS tornado goes from non-existent to ground contact in under 5 minutes, sometimes under 2. Radar algorithms designed to detect the rotating signature of a mesocyclone often miss QLCS rotation entirely because it never spends long enough at any single altitude to trigger the usual detection thresholds. And the timing is the other part of the problem. Squall lines peak in overnight hours precisely because the low-level jet strengthens after sunset. Into a strong low-level jet, into a sleeping population. The 40 million people inside the warning polygon on that night were not a uniform group facing identical risk. The risk was not spread evenly across 800 miles of alert boxes. It was concentrated in specific housing types, in specific locations, in specific communities, where the intersection of weather geography and human geography had been quietly building a dangerous equation for years. A person in a basement of a well-built house in suburban Minneapolis faces a fundamentally different risk profile than a person in a mobile home on the edge of a rural town in central Oklahoma. The atmosphere does not make that distinction. The statistics do. And the warning system itself, the infrastructure designed to bridge that gap between atmospheric reality and human awareness, was operating under conditions in 2026 that made its limitations more visible than they had been in years. The National Weather Service Chicago office had issued 128 warnings through mid-April. That is an enormous operational load. Experienced severe weather forecasters take years to train. They require specialized education, extensive hands-on experience with live radar interpretation, and the kind of pattern recognition that only develops through watching hundreds of storms develop in real time. When an office is handling near continuous severe weather for weeks, when the warning count is running at 3 to 4 times the historical average through this date, the question of whether the system has the capacity to maintain that pace without degradation becomes a real operational question, not a theoretical one. The Michigan outbreak earlier in the season had already raised that question in a very public way. A small tornado outbreak struck a 3-county area during a period when the Storm Prediction Center had rated the region at only marginal risk. Because the outbreak was geographically concentrated and developed quickly, the radar and forecasting tools had difficulty detecting the rotation early enough to issue a tornado watch in advance. No watch was issued. People died. The governor's office subsequently called for a formal investigation into why no tornado watch had been put into effect and whether proposed budget reductions to the National Weather Service had played any role in the forecast gap. Those questions were still being investigated when the next major pattern organized across the corridor and aimed itself at 40 million people. The radar network itself has known gaps that every forecaster understands and that most of the public has never thought about. The primary system, called NEXRAD, consists of roughly 160 high-powered Doppler radar sites distributed across the country. Each site can scan out to approximately 230 miles for precipitation. When you combine coverage from all sites, most of the country sits within range of at least one radar. But range is not the same as useful coverage. A radar beam does not travel flat along the surface of the Earth. As it travels outward from the antenna, the curvature of the Earth causes it to climb. At 50 miles from a radar site, the lowest beam is already several thousand feet above the ground. At 100 miles, it may be more than a mile up. At the edge of its range, the radar is scanning through the middle of the atmosphere, well above where a tornado forms and touches the ground. This geometry creates low-level coverage gaps across significant portions of the country. In those gaps, the radar may detect that a storm exists, may show its upper levels clearly, but the rotation near the surface, the rotation that is actually pulling air off the ground and turning it into a tornado, may be completely invisible to the scan. The known low coverage zones include parts of the Northern Rockies, sections of the Ozarks, stretches of the Mississippi River Valley, and areas of rural Alabama and Tennessee, where the nearest radar is simply too far away to see what is happening at low altitude. For the 40 million person corridor on that night, most of the geography was well covered. The Central Plains and the Midwest have relatively dense radar overlap, multiple sites with intersecting coverage areas that give forecasters multiple angles on the same storm. But well covered is a relative term, and the specific type of storm most likely to produce QLCS tornadoes in the overnight hours, embedded in heavy rain inside a fast-moving squall line, is precisely the storm type most likely to defeat even good radar coverage, because the tornado is wrapped in precipitation that makes it invisible to human eyes and difficult to detect with algorithms designed for clearer signatures. The storm does not need a radar gap to hide. It can hide in plain sight inside the rain. The financial exposure sitting inside that 40 million person corridor is a number that almost nobody in the public conversation about severe weather ever discusses. A 2026 report from CoreLogic, a major property analytics firm, identified more than 43 million properties across the United States at moderate or greater risk of damage from severe convective storms. The reconstruction cost value of those properties, the engineering price tag of replacing everything that could be damaged, sits at approximately $17.8 trillion. $17.8 trillion. That is larger than the annual economic output of most national economies. It is roughly 2/3 of the entire United States gross domestic product, and it is not a static number. It grows every year as the country continues to build homes, commercial facilities, data centers, warehouses, and renewable energy infrastructure in regions that the atmosphere keeps targeting. Texas carries the largest share of that exposure, but the metro area sitting at the top of the rankings for financial exposure per square mile is not in Texas. It is not in Oklahoma. It is not in any of the states that appear in the traditional mental image of tornado country. The metro area carrying more financial exposure to severe convective storms than any other in the country is Chicago. Approximately $1 trillion in reconstruction cost value concentrated in a single metropolitan region. $1 trillion. The mechanism is not primarily weather, it is density. Chicago is one of the most densely built metropolitan areas in the country. When a hailstorm or a derecho sweeps across that footprint, it damages an enormous number of structures simultaneously, without needing to be an unusually strong event. The storm does not need to be historic to produce historic losses. It just needs to hit the right zip codes. And Chicago, as the data from 2026 was demonstrating in real time, was a target the atmosphere kept finding. Illinois leading the country in all three severe weather categories simultaneously was not a coincidence. It was a signal. The same signal that researchers have been documenting for 2 decades in peer-reviewed literature about the eastward shift of tornado activity. The traditional alley was not disappearing. It was being supplemented by a new centre of gravity further east, further into populated territory, further into the zone where the old risk maps no longer accurately reflect what the atmosphere is actually doing. The insurance industry had already rebuilt its models to reflect this shift. Premiums in severe weather-exposed states had climbed substantially in the years leading up to 2026. In some markets, insurers had withdrawn from certain types of coverage entirely. Reinsurance companies had revised their treaties, and for homeowners in places like central Illinois or suburban Minneapolis or rural Oklahoma, the practical consequence showed up in annual premium notices that kept climbing regardless of whether their specific address had ever been touched by a storm. The models were pricing the trajectory, not just the history. They were pricing the fact that the corridor was shifting east, that the exposure was growing, that the atmosphere was delivering more severe weather to more populated areas than the 20th century maps had suggested was possible. The jet stream sitting above all of this was the single most important feature of the atmosphere in the days surrounding that warning. A ribbon of fast-moving air roughly 6 to 9 miles above the surface, driven by the temperature difference between the warm tropics and the cold polar regions, it had been locked in almost the same position for weeks. A deep trough carved into the western United States, air accelerating as it rounded the base of that trough and launched northeast across the plains, cold air spilling south along the western flank, warm Gulf air pulled north along the eastern flank, the collision zone sitting right over the corridor where 40 million people lived and worked and slept. The technical term for this kind of stuck pattern is a blocking event. The atmospheric systems refuse to move east at their normal pace. They stall. Weeks of weather happen over the same geography. Drought deepens in one region, while flooding builds in another. And in the case of severe weather, the same warm sector gets loaded, fired, and reloaded day after day after day. The Storm Prediction Center had been noting the persistence of this blocking pattern in their official forecast discussions for weeks. Their longer-range outlooks had repeatedly described what they were calling an active severe weather pattern expected to continue through the coming period. That language, repeated across multiple forecast cycles, is shorthand for a jet stream that will not budge. The reason it would not budge connects to a physics question that atmospheric scientists have been studying intensely in recent years. When a large temperature contrast locks into a particular geographic configuration, the jet stream tends to follow that contrast and reinforce it. The western United States had unusually cold air aloft. The Gulf of Mexico was unusually warm. The gap between those two extremes was sharper than a typical spring, and sharp gaps produce strong, stable wave patterns in the jet stream that resist the normal eastward progression of weather systems. There is another factor in the background of that stability, one that the scientific community has been debating with increasing urgency. The loss of Arctic sea ice has been proposed as a contributing mechanism to more frequent blocking patterns in the Northern Hemisphere. The research on this connection is not fully settled. Reasonable scientists disagree about the magnitude of the effect, but the observation that the jet stream has been exhibiting more persistent, more extreme wave patterns more frequently in recent decades is not in dispute. Whatever the deeper cause, the near-term consequence for the 40 million people under that warning was direct. A stuck jet stream meant the ingredients for severe weather kept showing up in the same places. Forecasters could not tell a town in Oklahoma to stand down just because it had been hit the previous week. Under a blocking pattern, the same town is often back in the crosshairs within days. The science connecting all of this to long-term climate change is more nuanced than most headlines capture, and more revealing than most dismissals acknowledge. Tornadoes are genuinely difficult to attribute to climate change directly. The tornado record in the United States depends heavily on changes in reporting over time. More observers, better radar, more storm spotters, more cell phones with cameras mean that tornadoes today are detected and confirmed at rates that make historical comparison complicated. What the research does show with more confidence is that several of the ingredients feeding severe weather have shifted in directions that, if anything, favour more intense events. Sea surface temperatures in the Gulf of Mexico have risen measurably. That warming increases the moisture content of the air flowing north into the severe weather corridor, raising dew points, increasing instability, pushing the fuel source further inland than historical averages. Atmospheric instability itself, the raw energy available for storms to explode upward, appears to have trended upward in some regions. Heavy precipitation events have become more frequent and more intense across the central and eastern United States, a trend consistent with basic physics about warmer air holding more water vapor. None of those signals individually proves that any specific tornado was caused by climate change. The statement "this tornado was caused by climate change" is not one that most climate scientists would make about any individual event. The statement "warmer Gulf waters have increased the moisture available to severe storms in the central United States," shifting the potential for intense events upward compared to the mid-20th century baseline, is one that most climate scientists would stand behind. The difference between those two statements matters enormously for how the public understands the risk. The first is a claim about causation of a specific event. The second is a claim about the background conditions against which all events now occur. The background has shifted. The gun is loaded differently than it used to be. Whether any specific storm pulls the trigger is still determined by weather, not climate. But the ammunition has changed. What does not appear to be changing, or not changing fast enough, is the built environment's response to the shifting risk. The country has been building itself further into the path for decades. Suburbs have expanded into former farmland across the Central Plains and the Midwest. Metropolitan areas have pushed outward into regions that were rural when the old risk maps were drawn. Interstate highways have pulled population centres closer together across the storm corridor, and in some parts of the country, entire new neighbourhoods have been constructed on ground that sits directly inside zones the atmosphere targets repeatedly. Each of those structures adds to the exposure number. Each of those new residents adds to the population inside the warning polygon. The 40 million figure is not a stable number. It is a number that grows every year, not because the storms are necessarily worse, but because there are more people and more structures in the path when the storms arrive. The specific corridor that was loading on that day in late April 2026 had a feature that made it particularly dangerous beyond the raw numbers. The cities along it are not evenly distributed. There are pockets of very high population density and pockets of sparse farmland sitting right next to each other. A tornado touching down in a cornfield outside of Des Moines becomes a number in a NOAA database. The same tornado touching down 3 miles east in a subdivision of Des Moines becomes a disaster declaration. The storms do not choose, the geography chooses. And the geography along the Oklahoma to Minnesota corridor in 2026 included several million people living in areas where the old mental model of tornado risk, the image of open plains and visible funnels and plenty of time to react, had never been accurate and was becoming less accurate every year. The specific mechanics of how a storm transitions from a discrete supercell into a squall line matter more than most viewers realise, because the transition itself is a trap. During the supercell phase, the atmosphere is producing its most organised, most trackable, most warnable threats. A rotating supercell announces itself on radar. The mesocyclone signature develops over time. Forecasters can watch the rotation tighten, can see the storm relative helicity values climbing, can issue a tornado warning with meaningful lead time because the storm has been telling its story for 30 or 40 minutes before anything touches the ground. That lead time saves lives. It is the product of decades of investment in Doppler radar technology, in forecaster training, in the kind of institutional knowledge that accumulates only through watching thousands of storms develop in real time and learning the language they speak before they become violent. But when the supercells begin to merge, when the individual storms lose their isolation and collide into a continuous line, the radar picture changes in ways that compress the warning timeline dramatically. The organised rotation that made the supercell readable disappears into the chaos of 1,000 updrafts and downdrafts competing along a front that might stretch 400 miles from end to end. What replaces it are brief, intense pulses of rotation embedded inside the line, forming and dissipating faster than the radar scan cycle can reliably detect them. The radar completes a full volume scan roughly every 4 to 6 minutes. A QLCS tornado can form, touch ground, travel half a mile, and lift in less time than it takes the radar to finish one complete scan. The warning that should precede it by 13 minutes might arrive with 2 minutes of lead time, or 30 seconds, or not at all. This is not a failure of technology in the sense that the technology is broken. It is a fundamental limitation of the physics of remote sensing. The radar is measuring backscattered energy from precipitation particles. It infers rotation from the difference in velocity between precipitation moving toward the antenna and precipitation moving away. When that rotation is embedded in a line of intense precipitation, when the signal is cluttered with returns from rain and hail falling at rates that push the radar's ability to differentiate between targets, the rotation signature can be masked, weakened, delayed in detection. Forecasters know this. They compensate with pattern recognition, with experience, with the kind of intuition that develops from watching squall lines move through their specific geographic region over many years. But intuition is not a substitute for lead time, and lead time is what QLCS tornadoes steal. The 40 million people in the warning corridor that night were distributed across a landscape where the transition from supercell to squall line would happen somewhere between 8 in the evening and 2 in the morning, depending on which part of the corridor you were in. The people in Oklahoma would see the supercell phase first, in daylight or early twilight, with relatively long warning lead times and the ability to see the storm approaching. The people in Iowa and Minnesota would see the squall line phase after midnight in total darkness, with compressed lead times and the additional vulnerability of being asleep when the warnings arrived. The risk was not uniform across the 800 miles. It was graduated, shifting from manageable to treacherous as the night progressed and the storm system evolved. The role of solar energy infrastructure in this picture is something that almost never appears in news coverage of severe weather events, but has become increasingly significant to the people who model catastrophic losses for a living. Utility-scale solar installations have expanded rapidly across Texas, the Plains, the Midwest, and the Southeast in the years leading up to 2026. These are vast arrays of photovoltaic panels, sometimes covering several thousand acres, generating electricity that feeds into regional grids, serving millions of customers. Their geography overlaps almost perfectly with the American severe weather corridor, and solar panels are vulnerable to hail in ways that the standard construction materials used in residential and commercial buildings are not. A standard utility-scale photovoltaic panel is tested to withstand hail up to approximately 1 inch in diameter. That specification is sufficient for the majority of hail events. It is not sufficient for the large hail events that had become a signature of the 2026 season. Earlier that year, a hailstorm in Illinois had produced stones measuring more than 6 inches in diameter. 6 inches? The size of a softball. A hailstone that size, falling at terminal velocity, strikes the ground at speeds approaching 100 miles per hour. It can punch through a vehicle roof. It can shatter a solar panel in a single impact. A field of 5,000 panels, all destroyed in 45 minutes by a hailstorm that moves through at 50 miles per hour, represents tens of millions of dollars in damage and a sudden reduction in grid capacity that ripples outward to customers who were not even in the path of the storm. The industry had begun responding to this exposure with tilting tracker systems that can angle the panels away from incoming hail, reducing the surface area exposed to impact. Some newer installations use panels rated for larger hail sizes, but the build-out of new solar capacity across storm-prone regions continued at a pace that outran the adaptation. More panels were going into the ground every month. More of them were landing in the corridor that the atmosphere kept targeting. The physics that produce 6-inch hail are an amplified version of the same physics that produce any hail. A hailstone begins as a tiny ice crystal high inside a thunderstorm, at altitudes where the air is already below freezing. The updraft carries it upward through zones of supercooled water droplets, water that is liquid despite being below the freezing point because it has not yet encountered a surface to freeze onto. When the supercooled droplets contact the ice crystal, they freeze instantly, adding another layer of ice. Each pass through the growth zone adds thickness. Each return trip through the updraft adds more. The limiting factor is the strength of the updraft. A weak updraft can only support small stones before they fall out of the storm. A strong updraft, fueled by high cape values and rich Gulf moisture and organised storm structure, can hold a growing hailstone in the growth zone for 10 or 15 minutes, cycling it through repeatedly until the stone has grown to a size that would have seemed implausible to a meteorologist from 50 years ago. The record hail sizes documented in the United States have been increasing over the record-keeping period. Whether that trend is driven primarily by improved detection and documentation or by genuinely changing atmospheric conditions is still being studied. What is not ambiguous is that the events themselves are happening, are being measured, and are producing damage at scales that the old actuarial tables were not built to handle. Flash flooding, the hazard that consistently kills more Americans per year than tornadoes do, was embedded inside the same storm system as a secondary threat that received a fraction of the public attention. The forecast mentioned it. The Weather Prediction Center had it flagged in their outlooks. But the cultural weight of the word tornado is so dominant in the American severe weather conversation that the flooding risk tends to recede into background noise, even when the numbers attached to it are just as deadly. 6 inches of moving water can knock an adult off their feet. 2 feet of moving water can float most cars and trucks and SUVs. And yet every year, in storm after storm, drivers attempt to cross flooded roadways that they believe they can navigate. And every year, the fatality reports list the same cause: vehicles swept off-road, vehicles submerged at low water crossing, occupants did not survive. The phrase "turn around, don't drown" has been the National Weather Service's primary flash flood safety message for years. It is short, it rhymes, it is correct, and it is ignored at a rate that produces a consistent, predictable, entirely preventable category of fatalities in every major storm event across the country. The reason it is ignored is not ignorance of the advice. Most drivers who attempt to cross a flooded road have heard the phrase. The reason is a failure of risk perception in real time. A road that normally carries 4 inches of water across a low crossing after heavy rain looks manageable. The driver has driven through it before after smaller storms. The road looks passable. What the driver cannot see is that this time the water is moving faster, is deeper at the centre of the crossing than at the edges, and is continuing to rise because a creek upstream crested 20 minutes ago, and the pulse of that crest has not yet reached this crossing. By the time the vehicle enters the water, and the driver feels the current trying to push the car sideways, the decision has already been made, and unmade it is too late. The storm system heading toward 40 million people on that night carried flash flooding potential across its entire eastern flank. The jet stream pattern that had been firing the same corridor for weeks meant the ground across Iowa, Illinois, and Indiana was already saturated from previous events. Soil that is already holding maximum moisture cannot absorb additional rainfall at its normal rate. Runoff accelerates. Streams respond faster to rainfall than they would under dry conditions. Flood crests arrive earlier and are higher than the rain alone would suggest because the ground itself has become an impermeable surface. Urban drainage systems designed for typical rainfall rates get overwhelmed. Streets that never flood become canals. Underpasses that look safe become death traps. And somewhere in that landscape, in the overnight hours when the squall line was pushing east and the QLCS tornadoes were spinning up and lifting before warnings could reach the people in their paths, someone was going to try to drive through a road that was underwater and was not going to make it to the other side. The population sitting inside that 40 million person warning zone was not a monolith in terms of access to information, access to shelter, or access to the kind of preparation that converts a warning into a survival decision. The Wireless Emergency Alert System, the federal infrastructure that pushes tornado warnings directly to cell phones in a warning polygon, represented a genuine improvement in the last decade of American warning technology. A tornado warning that would previously have depended entirely on sirens, on television broadcasts, on a neighbour banging on a door, could now reach a cell phone in a warning zone within seconds of the warning being issued. That improvement is real, and it has saved lives, but it has limits that compound in the overnight hours in ways that the daytime version of the same system does not face. Phones on silent mode may not produce an audible alert. Phones outside cellular coverage areas never receive the message. People in deep sleep may not be awakened by an alert that would be impossible to ignore while awake. The system assumes a level of baseline awareness and preparedness that is not uniformly distributed across 40 million people in 800 miles of warning polygon. The communities most exposed within that polygon shared several characteristics that researchers studying tornado vulnerability have identified consistently across decades of fatality data: rural location, greater distance from the nearest radar site, greater distance from the nearest permanent shelter, higher proportion of manufactured housing stock, and lower rates of weather radio ownership compared to urban and suburban areas. Weather radios, the dedicated devices that monitor National Weather Service broadcasts and activate automatically when a warning is issued, represent one of the most reliable, redundant alert systems available for exactly the scenario the overnight squall line was about to create. A phone can be silenced. A weather radio set to alert mode cannot be ignored by a sleeping person in a small house. The alarm is specifically designed to be loud enough to wake people. Studies of tornado fatality patterns have shown consistently that households with functioning weather radios have lower fatality rates in nighttime tornado events compared to similar households without them. The devices cost between $30 and $60. They are available at most hardware stores. They are owned by a small fraction of the households that would benefit most from having them. The preparation gap between what the warning system can deliver and what the population is positioned to receive is not a new problem. It has been documented in after-action reports from major tornado events going back decades. It has been the subject of recommendations from the National Weather Service, from FEMA, from academic researchers studying disaster preparedness. The gap persists not because the information about how to close it is unavailable, but because closing it requires sustained investment in community-level preparedness infrastructure that is unglamorous, that does not generate television coverage, and that tends to receive funding only in the immediate aftermath of a major event, when political attention is briefly focused on the problem before moving on. The storm system that was loading across the Central Plains in those final hours before it fired was not waiting for any of those gaps to close. The atmosphere does not operate on policy timelines. The jet stream trough was deepening. The surface low was intensifying. The dew points across the warm sector were climbing into the mid-60s as far north as southern Minnesota. The dry line was sharpening across the Oklahoma Panhandle as the afternoon heat differential between desert air and Gulf air reached its daily maximum. All four of the pattern elements that experienced forecasters recognize as the signature of a significant severe weather day were in place. They had been in place for more than 24 hours, which is why the Storm Prediction Center had been raising the risk level repeatedly and why the warning polygon had been redrawn 3 times. The atmosphere was not subtle about what it was doing. It was legible to anyone trained to read it. The question of whether the 40 million people inside the polygon would translate that legibility into action was a different question, one that the forecast system had no mechanism to answer. The economic machinery that responds to these events was already in motion before the first storm fired. Insurance adjusters were positioning across the region. Emergency management agencies in Oklahoma, Kansas, Missouri, Iowa, Illinois, Wisconsin, and Minnesota were pre-staging resources. Hospitals in cities along the corridor were reviewing their mass casualty protocols. FEMA regional offices were monitoring the forecast discussions and preparing to move into response mode if the damage crossed the threshold for a federal disaster declaration. Airlines had already begun rerouting flights away from the most active part of the corridor for the evening push. Trucking companies operating fleets through the Midwest were adjusting routing algorithms to avoid the predicted severe weather timing. All of that economic activity, that collective response to a forecast, represents an enormous amount of value created by the warning system before a single tornado touched the ground. Every flight that rerouted, every truck that took an alternate highway, every hospital that added staff to the overnight shift because the forecast suggested it was going to be needed, represented a cost avoided, a risk hedged, a consequence reduced by the existence of a system capable of seeing the storm coming with enough lead time to act. The $17.8 trillion in reconstruction cost value sitting inside the severe weather exposure zone is a backward-looking number. It measures what is already there. The forward-looking number, the trajectory of how that exposure is growing, is harder to calculate, but in some ways more important to understand. The country is not building at a reduced rate in severe weather zones. It is building at an accelerating rate. The population migration patterns of the 2010s and 2020s moved large numbers of people from the northeast and the west coast toward the Sun Belt and the plains and the southeast, precisely the regions where severe weather exposure is highest. Remote work, enabled by the same digital infrastructure that carries tornado warnings to cell phones, allowed households to relocate from cities where housing costs were prohibitive to regions where the same dollar bought significantly more space. Many of those relocations landed people in zones that their previous urban geography had insulated them from, zones where the severe weather risk was real, but where the cultural familiarity with that risk that develops over generations of living in tornado country was absent. A person who grew up in suburban Chicago or Boston or Seattle and moved to a rural county in central Oklahoma or southern Illinois in their 30s does not carry the same intuitive understanding of severe weather that someone whose family has lived in that county for 3 generations carries. The knowledge of which direction to watch the sky, which clouds to take seriously, how much time you actually have between a tornado warning and a storm arrival, given your specific geography, what the sirens in your specific town sound like versus the test sirens, where the nearest shelter actually is when you need it in the middle of the night. That knowledge is not transmitted by a weather app. It accumulates over years of experience in a specific place. And the rapid population redistribution that had been underway across the country for more than a decade had deposited millions of people in high-risk geographies without that accumulated local knowledge, dependent entirely on systems and devices and warning infrastructure that worked well on average, but that still had gaps precisely where local knowledge would have bridged them. The Lena tornado from April 17th was an example of the warning system working as designed. The Storm Prediction Center had issued a moderate risk for that region. Radar operators tracked the parent supercell for more than an hour before it produced the tornado. Warnings went out, sirens sounded, cell phones alerted. People who had working weather radios received the alarm. Most residents of Lena survived because the warning system functioned and because most of them were awake and able to act on the warning. The median tornado warning lead time in the United States is approximately 13 minutes. 13 minutes is enough time to reach a basement or an interior room if you are awake, if you hear the warning, and if you move immediately without stopping to look out the window, without calling a family member to confirm what you heard, without checking a second app to see if the warning is real. 13 minutes is the median. For some storms it is 30. For QLCS tornadoes embedded in overnight score lines, it can be 3, or 1, or 0. The corridor that was now loading across 800 miles of the central United States had in its forecast the full menu of these scenarios playing out sequentially over roughly 12 hours. Supercells in the afternoon and early evening, with relatively long lead times, merger into score line structure after dark. QLCS tornadoes in the overnight hours, with compressed warning windows. Flash flooding across the eastern portions as the heaviest rain moved through saturated ground. And then, in the pre-dawn hours as the system pushed into the Great Lakes region, the possibility of embedded rotation continuing into areas where radar coverage was slightly less dense and where the population, exhausted from a night of alerts, might have begun to let their guard down in the hours just before dawn. The forecasters watching all of this from their screens at the Storm Prediction Center in Norman, Oklahoma, and at local forecast offices stretching from Tulsa to Minneapolis, were doing what they are trained to do: watching the radar, reading the soundings, evaluating the model output, writing the forecast discussions in the careful, calibrated language that the institution has developed over decades to communicate threat levels without overstating or understating what the atmosphere is likely to produce. The language in those discussions on that day used phrases that experienced readers of National Weather Service text recognize as meaningful. Effective layer shear supporting supercell thunderstorms, CAPE values supportive of intense convective development, low-level jets strengthening into the overnight hours, QLCS tornado potential increasing after midnight. Every one of those phrases pointed toward the same conclusion. The storm had been underestimated at the beginning of the season, and it was not finished making its case. The Pacific Ocean had been part of the story since before any of the 2026 storm season began, though most of the people in the warning polygon had no way of knowing that. The tropical Pacific had been running in its cool phase, La Niña, for the better part of 3 years. La Niña conditions tend to shift the jet stream further north than average across North America, which pulls the clash zone between cold and warm air deeper into the interior of the continent. Research on severe weather patterns during La Niña years has shown consistently that these years tend to run hotter than average in terms of severe weather activity. with some years producing tornado counts well above the historical baseline. The spring of 2026 had been a textbook La Niña spring in that regard. The jet stream locked in its northward shifted position, the same corridor fired again and again. The Storm Prediction Centre's enhanced risk days had accumulated at 3 to 4 times the historical rate through mid-April. The entire front-loaded character of the season, the record warning counts, the Illinois tornado totals, the Chicago anomaly in financial exposure, all of it traced back in part to a sea surface temperature anomaly in the equatorial Pacific that most Americans had never heard of. But that cool phase was ending. Oceanographers monitoring subsurface water temperatures in the tropical Pacific had been tracking a Kelvin wave, a pulse of warm water moving eastward along the equator, for months. By late April 2026, that warm water was beginning to surface in the eastern Pacific. Trade winds were weakening. The signs of an El Niño transition were accumulating in the ocean data, even as the La Niña atmospheric pattern continued to drive severe weather across the central United States. The atmosphere lags the ocean by weeks to months. The jet stream configuration that had been producing the most active severe weather season the Chicago office had ever recorded through this date in the year was still a La Niña jet stream, even as the ocean underneath was transitioning away from La Niña conditions. That lag is why the next 6 weeks still mattered enormously for the total character of the 2026 season. May is historically the most active month for severe weather in the United States. The 30-year average tornado count for May runs around 300, more than any other month by a significant margin, and the jet stream configuration producing the spring of 2026 had not yet released its grip on the pattern. Long-range forecasts from multiple meteorological services were already identifying the potential for additional significant severe weather events in the weeks following the 40 million person warning. The models were showing subsequent troughs digging into the western United States, subsequent surface lows developing across the plains, subsequent warm sector setups along the same general corridor that had been firing all season. The storm heading toward 40 million people was not the last storm of the season. It was not even close to the last storm. It was the current pulse in a pattern that showed no immediate signs of breaking, in a season that had been running well ahead of the long-range forecasts that predicted a quiet year, in a corridor that had already broken records and was still adding to them. The specific question that forecasters could not answer, the one that determined whether this particular event would join the list of remembered outbreaks or fade into the statistical noise of an already extraordinary season, was where the supercells would track during that critical early evening window. A track that kept the most intense storms over rural western Kansas and Nebraska would produce dramatic radar loops, impressive storm chaser footage, and relatively limited structural damage because the population density in those areas is low. A track that pushed the supercells slightly further east into the suburban rings of Wichita or Kansas City or Des Moines would translate those same atmospheric ingredients into a much larger damage footprint and a much larger human cost. The difference between those two scenarios was not a question of how strong the storms would be. The storms were going to be strong regardless. The difference was purely geographic. Where exactly would the most intense rotation occur relative to where people were sleeping? That question was still unresolved when the first storms began to fire along the dry line across western Oklahoma in the mid-afternoon. Discrete supercells, just as the forecast had indicated, standing alone on the radar with the sharp edges and organised structure that experienced storm chasers recognise immediately. The rotation signatures began appearing within an hour of initiation. Mesocyclone indicators lit up on the radar screens at the Norman Forecast Office. Tornado warnings went out for rural portions of the Oklahoma Panhandle. The storms were tracking northeast, as expected, parallel to the warm front, pulling in moisture from the Gulf sector to their southeast and pushing outflow to their northwest. The initial track looked favourable in the sense that the most intense rotation was over relatively sparse terrain. But the tracks were shifting slightly with each update, and slightly, over the course of 800 miles of corridor and 12 hours of storm evolution, is a word that can mean everything. The first tornado warning of the evening was issued at 4:47 in the afternoon for a rotating supercell that had been tracking northeast across the Oklahoma Panhandle for just over 90 minutes. The rotation signature on radar was unambiguous. The mesocyclone had been tightening for 20 minutes before the warning went out, giving forecasters at the Norman office enough confidence to issue, with a lead time of roughly 18 minutes before the circulation reached the nearest town in the warning polygon. 18 minutes is above average. It is enough time for a prepared household to move to shelter, for a school to execute its tornado drill, for a farm family to get from the barn to the basement. It is not enough time for someone who hears the warning and then spends 4 minutes trying to confirm it on their phone, 2 minutes waking up a family member, 3 minutes looking out the window to see if they can spot anything, and 4 more minutes arguing about whether this one is really serious or just another false alarm from a system that has been issuing warnings all season long. The warning fatigue problem is real, and it is documented. Research on public response to tornado warnings has shown consistently that the probability of taking protective action decreases as the number of warnings a person has experienced without a tornado striking their immediate location increases. People who have been in a warning polygon 10 times and never experienced a tornado are measurably less likely to respond quickly to the 11th warning than people experiencing their first or second. The 2026 season, with its extraordinary volume of warnings, its record-setting pace across the Chicago office and the offices stretching from Tulsa to Minneapolis, had been building warning fatigue across the central corridor all spring. The people most in need of responding quickly to the warnings that evening were precisely the people who had been hearing warnings all season long without having a tornado land on their specific address. The second supercell to fire, about 40 miles south of the first, developed more slowly but ultimately organized into a more dangerous structure. By 6 in the evening, it had a persistent mesocyclone signature that had been present for more than 30 minutes without dissipating, which is a meaningful indicator of storm quality. Storms that maintain rotation for extended periods are more likely to produce significant tornadoes than storms whose rotation comes and goes. The atmospheric instability feeding this storm, measured by research aircraft flying into the inflow region, was running near the top of the forecast range. Cape values in the immediate environment of the storm were approaching 2,800 joules per kilogram. The low-level wind shear was strong. The storm was pulling in air from the warm sector with dew points in the mid-60s, and the updraft was using that fuel efficiently, punching through the capping inversion that had briefly suppressed storm development in the early afternoon and erupting into an anvil that spread downwind for more than 100 miles. The capping inversion is worth understanding because it plays a role in severe weather that almost never gets explained to a general audience, despite being one of the most important features of the pre-storm atmosphere. It is a layer of warm air sitting a few thousand feet above the surface that acts like a lid on the instability below it. During the morning and early afternoon of a significant severe weather day, the cap suppresses storm development. The atmosphere wants to fire, but cannot punch through the warm layer above. This is actually beneficial because it allows the instability to continue building, allows the moisture to continue pooling in the warm sector, allows the shear to continue organizing. Then, as the afternoon heat reaches its maximum and the jet stream disturbance approaching from the west erodes the cap, the lid comes off. The atmosphere, which has been trying to fire all day, erupts in the span of minutes. Storms that have been absent from the radar suddenly appear and intensify rapidly because they are building into an atmosphere that has been loading energy for hours. The more effective the cap during the day, the more explosive the initiation when it finally breaks. On that day across western Oklahoma, the cap had been strong enough to suppress development until just after 4 in the afternoon, which meant the atmosphere had been loading for the full afternoon heating cycle before the first storms fired. The energy available was near the top of what the forecast had suggested. By 7 in the evening, 3 discrete supercells were tracking northeast across the Kansas-Oklahoma border region. All 3 had active mesocyclone signatures. 2 had received tornado warnings in the previous hour. The tracks were converging slightly, which created a scenario forecasters watch carefully because supercells interacting with each other can behave in unexpected ways. Sometimes the interaction causes one storm to weaken as the other dominates. Sometimes the interaction produces a brief period of extreme organization as the 2 storm systems merge their circulations. The second scenario is rarer, but it is the one that produces the most violent tornadoes, the ones that stay on the ground for dozens of miles, that achieve widths of a mile or more, that produce the kind of damage that changes a community permanently. The Storm Prediction Centre's real-time products, publicly available online and used by emergency managers, news organisations and storm chasers simultaneously, were being updated every few minutes as the evening evolved. The mesoscale discussion documents, which provide forecasters running interpretation of what the atmosphere is doing between formal outlook updates, had taken on a tone that people who read them regularly recognised as elevated concern, expressed in the institution's characteristically restrained language. Phrases like particularly dangerous situation were appearing in the discussions. The PDS designation, reserved for tornado watches where the potential for long-track significant tornadoes is elevated above the normal tornado watch criteria, was being discussed internally for the region east of the initial supercell tracks. A PDS tornado watch is not issued casually. It signals to emergency managers that this is not a routine severe weather event, that the atmospheric ingredients are aligned for potentially historic tornado production, that the response level should match the threat level. The watch was issued at 7:42 in the evening for a region covering portions of Kansas, Missouri, and Iowa. The wording included the phrase, capable of producing strong and violent tornadoes, and listed effective wind shear values and CAPE numbers that sat at the upper end of what the atmosphere had produced all season. Emergency managers across the watch area escalated their posture immediately. County emergency management offices began sending staff alerts. Television meteorologists in Kansas City and Des Moines and Omaha interrupted programming to go live with storm coverage. The National Weather Service websites for the offices covering the watch area saw traffic spike to levels that temporarily slowed server response times. Every one of those responses was triggered by a text document issued from an office in Norman, Oklahoma, describing the state of the atmosphere over a region the size of several European countries. The storms continued tracking northeast through the evening hours. The track that had initially looked favourable, keeping the most intense rotation over sparse terrain west of the major population centres, began shifting. Subtle changes in the upper-level wind pattern, a slight ridge building to the north that deflected the storm tracks a few degrees eastward, were enough to redirect the most active supercell toward the suburban fringe of Wichita. The shift was small in angular terms. On the ground, the difference between the original track and the adjusted track was the difference between a tornado crossing a wheat field and a tornado crossing a neighbourhood of 3,000 homes. The Wichita metropolitan area sits in a particularly exposed position relative to severe weather climatology. It lies almost exactly in the traditional heart of the Southern Plains severe weather corridor, the zone where dew points from the Gulf regularly clash with cold frontal passages from the west. The city has a long history of tornado events, including a significant tornado in 1971 that caused widespread damage across the city's south side and killed 16 people. But the Wichita of 2026 was significantly larger than the Wichita of 1971. The population had grown. The suburban footprint had expanded in every direction, pushing new residential development into areas that were farmland when the 1971 storm occurred. The exposure had grown. The memory of that previous event had faded for most current residents, replaced by the generic awareness that yes, this is tornado country, but it hasn't really hit us in a long time. The tornado warning for the southwestern suburbs of Wichita was issued at 8:53 in the evening. Radar indicated rotation that had been present for 11 minutes prior to the warning, with the circulation tightening rapidly in the final 4 minutes before issuance. Lead time from warning to first ground contact was estimated at 9 minutes, based on storm motion and the distance to the nearest populated area in the path. 9 minutes is below the national median of 13. It is enough time for someone who was already in their shelter, who had made the decision to take cover when the PDS watch was issued 2 hours earlier, rather than waiting for a specific warning for their specific location. It is not enough time for someone who was cooking dinner and looked at their phone at the alert sound, and then stood in the kitchen reading the warning text to figure out exactly which street the warning covered and whether that street was close enough to their street to matter. The tornado that touched down southwest of Wichita at 9:02 in the evening was rated EF3 after survey teams completed their damage assessment in the days that followed. EF3 winds between 136 and 165 miles per hour are enough to destroy well-built homes with complete wall collapse on all sides, to overturn and destroy trains, to uproot trees and carry them significant distances. The damage path was approximately 400 yards wide and extended for 11 miles before the tornado lifted. 11 miles in the suburban landscape southwest of Wichita. A path that wide, covering that distance, in an area with that population density, touching houses on both sides of roads that ran perpendicular to the track, produces a damage toll that accumulates faster than any single statistic can capture. Structures on one side of a street with minor damage, structures on the other side reduced to their foundations. The randomness of the damage pattern within the swath, which appears uniform from satellite imagery, contains 1,000 individual stories of inches and angles, and where someone happened to be standing in relation to which wall held and which one failed. 11 miles northeast of where the Wichita tornado lifted, the second supercell was tightening its rotation over the open farmland of central Kansas, still tracking northeast, still maintaining the kind of persistent mesocyclone structure that kept it on the watch list of every forecaster monitoring the event. This storm had been rotating for more than 2 hours without producing a confirmed tornado, which is unusual for a supercell of its radar presentation quality. Storms that rotate intensely for extended periods without producing a tornado sometimes do so because atmospheric conditions just below the storm base are slightly too stable to allow the rotation to extend to the ground. A thin layer of relatively cool, stable air just above the surface can act as a buffer between the intense rotation in the mesocyclone and the ground contact needed to produce a tornado. This buffer can break down suddenly, without obvious warning on the radar, producing a tornado that seems to appear from nowhere because the preceding period of rotation had not resulted in ground contact. At 9:27 in the evening, the second supercell produced its first tornado. The initial contact was in open farmland north of Great Bend, Kansas. The rotation that had been building for more than 2 hours concentrated into a circulation that was, by radar velocity estimates at the time, producing winds exceeding 180 miles per hour at the surface. The tornado widened quickly as it moved northeast. Within 5 minutes of initial contact, it was estimated at 3/4 of a mile wide. Moving at 35 miles per hour northeast, it had a path that, if it maintained its track and did not lift, would carry it across portions of central Kansas and into the southwestern corner of the Kansas City metropolitan region before midnight. The warning chain that followed was among the most intense sustained severe weather warning sequences the Wichita National Weather Service office had ever produced. In the space of 90 minutes, the office issued or updated more than 40 individual warnings covering portions of 7 counties. Each warning required a forecaster to evaluate the current radar data, assess the threat, write the warning text, verify the geographic polygon, and issue it through the official communication systems that push the alert to cell phones, weather radios, and broadcast partners simultaneously. 40 warnings in 90 minutes is a pace that pushes the limits of what a fully staffed office can maintain without errors. The office was not at full staff that evening. 2 of its positions were vacant, the result of a hiring freeze that had been in place for several months, pending budget clarification from the federal level. The forecasters who were present were performing at the level their training demanded, but they were doing it with fewer hands than the scenario warranted. This is the staffing gap that had been the subject of quiet concern within the meteorological community for years before the Michigan outbreak brought it briefly into the news cycle. The National Weather Service operates on a staffing model that was designed around the warning load of a typical severe weather season. 2026 was not a typical severe weather season. It had been running at extraordinary tempo since early March, and the tempo had not let up. The forecasters at offices across the central corridor were experiencing the kind of sustained operational intensity that produces cognitive fatigue over days and weeks, not the kind of acute pressure that a single major event produces. Sustained fatigue is subtler and in some ways more dangerous, precisely because it is harder to recognize and harder to accommodate in real time. The Kansas City metropolitan area had been watching the track of the second supercell with the specific anxiety that comes from living in a city that knows it sits in severe weather country and that has the financial and logistical infrastructure to respond, but that has never been directly hit by a violent tornado within its densest urban core. The city's emergency management apparatus was well-funded, well-trained, and well-coordinated. The county and municipal emergency managers had been in close contact with the Wichita and Kansas City National Weather Service offices since the PDS watch was issued. Shelter-in-place advisories had been pushed through the city's emergency notification systems. The major hospitals on the southwestern side of the metro had activated their mass casualty protocols. The fire departments in the path counties had pre-positioned resources. All of that preparation was the result of a warning system functioning at a high level, providing enough lead time for institutional responses to mobilize, even in the face of a fast-moving event. The individual response across the metro was less uniform. In the well-resourced suburban neighborhoods on the southwestern edge of the city, most households had access to basement shelter, had received the cell phone alerts, and had the cultural familiarity with severe weather preparation that living in tornado country for years provides. In the older neighborhoods closer to the urban core, basement availability dropped significantly. Housing stock built before 1960 in many Midwestern cities was constructed with full basements. Housing stock built between 1960 and 1995 often was not, depending on the soil conditions and construction practices prevalent in specific neighborhoods during specific decades. And in the mobile home parks and manufactured housing communities that existed on the periphery of the metro, in the areas where land was affordable and the housing stock was accessible to lower-income residents, the shelter gap was absolute. No basements, no interior rooms capable of providing meaningful protection against EF3 winds. The only safe option was to have left before the storm arrived. The tornado that had been moving northeast from central Kansas was still on the ground at 10:51 in the evening when it crossed into the Kansas City metro region from the southwest. It had been on the ground for 1 hour and 24 minutes, a duration that put it in the category of long-track tornadoes, events that are rare in absolute terms, but that have an outsized impact both on the landscape they cross and on the public memory of the regions they affect. Long-track tornadoes are rare because the atmospheric conditions required to sustain a tornado for that duration without the storm structure disrupting the surface circulation are specific and demanding. The storm must maintain its organisation. The thermodynamic environment must remain supportive. The wind shear must remain adequate through the depth of the storm. Any significant disruption to any of these ingredients tends to cause the tornado to cycle, lifting temporarily and then potentially reforming, or to weaken and dissipate entirely. The fact that this tornado had been on the ground for more than 80 minutes without dissipating was a statement about the quality of the atmospheric environment it was moving through. The storm was moving through exactly the kind of loaded, fuel-rich, high-shear environment that the forecast had identified and that the warning system had been alerting the public about for 2 hours before the first ground contact. The damage assessment in the days following the event was extensive. Survey teams from the National Weather Service, supplemented by engineers and structural experts brought in from the university system and from private forensic engineering firms, spent 4 days covering the full length of the damage path. The final report listed the rating as EF3 along most of the path, with a brief segment northeast of the initial touchdown area where damage indicators suggested winds exceeding the EF3 threshold, potentially approaching the lower boundary of EF4 classification. The EF4 designation requires winds of between 166 and 200 miles per hour, strong enough to level well-built homes with no remaining structure, to generate airborne debris that travels miles from the point of origin, to destroy reinforced masonry structures that are designed to withstand extreme loads. The damage in that segment was consistent with those thresholds. Several structures that had been built to modern code requirements, with engineered lumber connections, hurricane strapping, and reinforced sheathing, showed the kind of failure patterns that engineers use to distinguish EF3 from EF4 damage. The final official rating for the peak intensity segment was listed as high-end EF3, the same diplomatic language used for the Lena tornado earlier in the season. Language that places the event just below the next category, while acknowledging that the physical evidence was consistent with conditions approaching that threshold. The broader storm system was meanwhile completing its transition from supercell to squall line across the northern portion of the corridor. By 11 in the evening, the discrete supercells that had been tracking northeast across Kansas were beginning to merge with a developing line of storms pushing southeast from Nebraska. The merger was visible on radar as the sharp individual cell structures began to blur into each other, the isolated rotating towers losing their discreteness and becoming segments of a longer, more continuous front. The tornado threat from individual supercell mesocyclones was decreasing as this transition occurred, but the QLCS tornado threat, the embedded, short-lived spin-ups that form and dissipate inside the leading edge of a score line, was increasing, and midnight was approaching across Iowa and Wisconsin and northern Illinois, where the score line would arrive in the hours when the population was most asleep and least able to respond. The low-level jet that the forecast discussions had been flagging all day was strengthening exactly as predicted. Winds at roughly 3,000 feet above the surface across Iowa and Illinois were accelerating into the overnight hours, reaching speeds above 60 knots in some areas. 60 knots at low levels feeding into a score line is a significant energy source. It keeps the line alive, keeps the updrafts vigorous, keeps the leading edge of the system capable of producing new rotation pulses, even as the parent supercell structure that had been visible earlier in the evening was now buried inside the larger organised system. The score line pushing into Iowa at 11:30 carried with it the remnant energy of the supercells that had built and organised all afternoon and evening across Oklahoma and Kansas. The atmosphere had been working on this system for more than 8 hours. It had not finished. The first QLCS tornado warning across Iowa was issued at 12:17 in the morning. A brief rotation signature had appeared on radar at the leading edge of the score line near the town of Osceola in southern Iowa. The warning lead time was 4 minutes. 4 minutes from warning issuance to estimated ground contact based on storm motion. Most of the population of Osceola was asleep. The cell phone alerts went out, the weather radios activated for households that had them. The sirens sounded across the town. 4 minutes is enough time for a person who is already awake, already oriented, already knows exactly where their shelter is, to reach safety. It is not enough time for someone pulled from deep sleep by an unfamiliar alarm to fully process what is happening, locate their family members, move through a dark house without furniture collisions, open the basement door, navigate the stairs, and reach the lowest interior point of the structure before the storm arrives. The tornado that touched down near Osceola was brief and relatively weak, an EF1 by post-event survey, with winds estimated between 96 and 110 miles per hour. It was on the ground for less than 2 minutes and travelled approximately 3/4 of a mile before lifting. The damage it produced in those 2 minutes to a cluster of homes on the northern edge of the town represented losses that would take years for the affected families to recover from. Insurance claims, structural assessments, displacement while repairs were completed, the particular psychological weight of having your home partially destroyed while you were inside it in the middle of the night. None of that damage appeared in the broadcast coverage of the event the following morning, which focused entirely on the EF3 track near Kansas City and the damage footage from the Wichita suburbs. The Osceola tornado was a footnote in the statistics of an event that produced more than 30 confirmed tornadoes total across the 12-hour period. But it was not a footnote for the families whose houses it crossed. The score line continued pushing east-southeast through the overnight hours with the regularity and relentlessness of a machine that had been given fuel and told to run. QLCS rotation signatures appeared and disappeared along its leading edge at intervals of 20 to 40 minutes, some producing warnings, some dissipating before the rotation signature met the threshold for warning issuance, some producing tornadoes that were not detected in real time and were only confirmed by ground survey teams the following day. The total count of tornadoes from the overnight score line phase was difficult to establish precisely in the hours after the event, because the density of events and the distribution across a wide area made comprehensive survey coverage challenging. Preliminary reports in the first 24 hours after the storm system pushed through listed 14 possible tornado tracks from the score line phase. The final survey count, completed over the following week, confirmed 22. The flash flooding that accompanied the score line through Iowa, Illinois, and Indiana in the pre-dawn hours produced its own fatality record, separately from the tornado events. Rainfall rates in the heaviest precipitation bands exceeded 3 inches per hour in some locations. Ground that had been saturated from previous events earlier in the week could not absorb rainfall at anywhere near that rate. Creeks that were already running above normal levels crested again with the new rainfall and pushed water across roads that had dried out from the previous event just days before. Across a stretch of north-central Illinois between midnight and 4 in the morning, 6 different low water crossings recorded water depth sufficient to float a standard passenger vehicle. 2 of those crossings were on roads that lacked adequate warning signage. 2 others had warning signage that was in place but not illuminated. One was on a road that had been travelled hundreds of times by residents of the adjacent rural community without incident, and that had never previously flooded to dangerous levels in the 30-year memory of the community's longest-term residents. The atmospheric pattern of 2026 had produced rainfall accumulations that exceeded what anyone's local memory suggested was the normal envelope of possibility. The fatality associated with the flash flooding on that road occurred at 2:44 in the morning. A pickup truck attempting to cross the flooded section was swept off the road by water that the driver could not have assessed accurately in darkness at speed. The vehicle travelled approximately 80 feet downstream before coming to rest against a fence line in a farm field adjacent to the road. The driver was recovered by emergency personnel several hours later. This death, like the Osceola tornado, did not appear prominently in the coverage of the event. It was listed in the official National Weather Service storm data entry for the event as one of the 37 weather-related fatalities attributed to the system across its full 12-hour path. 37. A number that represents 37 individual human stories, 37 sets of people who woke up on the morning of that day and did not expect it to be their last. 37 communities processing the specific grief of losing someone to something that was forecast, that was warned about, that was visible on radar for hours before it arrived. The morning after a major severe weather event has a particular character in the communities it has touched. The immediate danger has passed. The adrenaline that sustained emergency responders through the overnight hours begins to ebb. The scope of the damage becomes visible in daylight for the first time. Neighbours emerge to assess what the darkness had obscured. The sounds of chainsaws replace the sounds of sirens. Structural engineers begin their walkthroughs. Insurance adjusters start scheduling site visits. And the larger machinery of disaster response, the coordination between local emergency management and state agencies and FEMA, begins the methodical process of translating the atmospheric event into an administrative reality that can be responded to through the federal disaster declaration process. The total insured loss from the 40 million person storm event was estimated in the weeks following at approximately $11 billion. That number placed it among the most costly severe weather events in United States history by insured loss metric, though it sat below the threshold of the truly catastrophic events that occasionally approach or exceed $50 billion. The $11 billion reflected primarily structural damage, with hail damage to vehicles and roofing systems comprising the largest single component, followed by wind damage to commercial and industrial structures, followed by residential structural losses from the tornado tracks. The flash flooding losses were partly covered under separate flood insurance policies, where they existed, but a significant portion of the flood losses fell in the gap between standard homeowner coverage and flood insurance coverage, leaving affected households facing costs that neither policy would fully address. The $11 billion figure was processed by the insurance industry as a significant but manageable event within the context of the 2026 season as a whole. The season had already produced multiple multi-billion-dollar events before this one. The cumulative loss total for severe convective storms in the United States through late April of 2026 was running well above the 10-year average. Reinsurance treaties that set the thresholds at which insurance companies begin drawing on their reinsurance coverage had already been triggered multiple times in the season by earlier events. The reinsurers who absorbed the excess losses above those thresholds were recalibrating their models in real time, feeding the loss data from each successive event back into the actuarial frameworks that would determine pricing for the following year's treaty renewals. The cascade from atmospheric event to insurance event to reinsurance event to treaty renegotiation to premium adjustment to household budget impact was playing out on a timeline of months, largely invisible to the public, but representing one of the most significant financial consequences of the 2026 severe weather season outside of the direct property damage itself. The political response to the season unfolded on a parallel timeline that intersected with the operational reality of the warning system in ways that were sometimes productive and sometimes not. Congressional hearings were scheduled in the weeks following the major April events to examine the state of National Weather Service staffing and funding. The Michigan outbreak, where the absence of a tornado watch had preceded fatalities, provided a specific focal point for the hearings that the more general concern about staffing levels had previously lacked. Representatives from districts in the storm corridor, Republicans and Democrats alike, found the issue one of the few that crossed the political divisions of the moment, since severe weather does not discriminate by voter registration, and the financial impact of inadequate warning infrastructure falls on constituents of both parties. The testimony from National Weather Service directors and from the union representing Weather Service employees painted a picture of an institution managing a growing operational load with resources that had not kept pace with the growth. The specific numbers presented at those hearings were stark. Vacancy rates at local forecast offices across the country averaged above 12%. In some offices, particularly those in rural areas where housing costs and quality of life considerations made recruitment difficult, vacancy rates were substantially higher. The hiring process for meteorologists required to staff those positions was slow, constrained by federal hiring regulations that moved on timelines measured in months and that were poorly adapted to the kind of targeted, urgent recruitment that a significantly understaffed institution needed. Training pipelines for new hires added additional months before a new employee could function independently on a warning desk during an active severe weather event. The result was a system that could not rapidly convert additional funding into additional operational capacity, even when the funding was available, because the human capital required to deploy that funding took years to develop. The atmospheric science community, meanwhile, was processing the 2026 season through the lens of the research questions it was generating. The front-loaded character of the season, the extraordinarily high warning counts through mid-April, the eastward displacement of the most active tornado tracks, the record hail sizes, all of these were data points being incorporated into ongoing research programs studying the behaviour of severe weather under changing atmospheric background conditions. The relationship between Gulf of Mexico sea surface temperatures and the frequency and intensity of significant tornado outbreaks was a particularly active area of investigation. Models that incorporated sea surface temperature data from the Gulf showed skill in predicting the general level of seasonal severe weather activity weeks in advance, beyond the range of traditional numerical weather prediction. That skill was not perfect. The models could not tell a forecaster which specific day in May would produce the next major outbreak, but they could tell a researcher in January, with meaningful probability estimates, whether the coming spring severe weather season was likely to be above or below average in total activity. In 2026, those models had suggested an above-average season. The forecasts issued to the public in early spring had suggested a near-average or slightly below-average season. The atmosphere had agreed with the research models, not with the public forecasts. That divergence was a subject of internal discussion within the meteorological community that rarely reached the public conversation, but that had real consequences for how preparedness resources were allocated in the weeks before the season began. Emergency management agencies that plan their resource pre-positioning and staff augmentation decisions based on seasonal outlooks had planned for a near-average year. When the season ran hot from the beginning, those plans had to be revised in real time, adding friction and cost to a response apparatus that worked most efficiently when it could prepare in advance rather than adapt on the fly. The lesson being drawn within the community, one that was likely to influence how seasonal outlooks were communicated in future years, was that the uncertainty bounds around those seasonal forecasts needed to be communicated more explicitly, and that the range of possible outcomes needed to be conveyed alongside the central estimate in a way that allowed emergency managers to plan for the more active end of the range, even when the central estimate suggested a quieter year. The El Niño that was developing in the Pacific as the spring of 2026 unfolded was expected to begin reshaping the atmospheric pattern over the second half of the year. A strong El Niño tends to shift the jet stream southward across North America, pulling the storm track further south and modifying the Gulf moisture patterns that feed severe weather in the central corridor. Historically, strong El Niño years have produced more active severe weather in some southern states during the fall, while reducing activity across parts of the central plains. The transition between those two patterns, the period when the La Niña atmosphere is giving way to an El Niño atmosphere, can itself be a period of unusual instability in the jet stream, with sharper troughs, more extreme wave amplitudes, and the potential for severe weather events that fit neither the La Niña pattern nor the El Niño pattern, but instead reflect the instability of the transition itself. The weeks of May and into June that the 2026 season still had ahead of it were precisely that transition period. Long-range forecasters watching the model output for the weeks following the 40 million person event were identifying signals consistent with at least 2 additional significant severe weather setups during the remainder of May. The details were uncertain at that range. Specific dates, specific corridors, specific intensity levels were beyond the reliable forecast horizon. But the general character of the pattern, the persistence of the jet stream configuration that had been driving the season, combined with the continued availability of Gulf moisture and the transition period instability being introduced by the El Niño development, suggested that the atmosphere was not done. The season that had already rewritten the record books for the Chicago Forecast Office, that had already displaced Illinois to the top of the tornado, hail, and wind report rankings, that had already produced the front-loaded outbreak sequence that the long-range forecasts had not anticipated, had more to say. The 40 million people who had been inside the warning polygon were now on the other side of the event. Some of them were assessing damage, some were filing insurance claims, some were in hospitals. Some were beginning the months-long process of rebuilding a home that a tornado had reduced to its foundation in seconds. Some were attending funerals, and a very large number of them, the majority, had passed through the event without direct impact, had received the warnings, had taken shelter or not taken shelter, and had emerged the next morning to find that the storm had passed their specific address without touching it. For those people, the natural human response was to recalibrate. The storm had come, the storm had passed. Their house was intact. The warning had been real, but the outcome for them personally had been benign. That recalibration is a survival mechanism. It is also a vulnerability. The person who passes through a severe weather warning without direct impact is statistically more likely to be inside the next warning polygon than the person who was directly hit by a tornado this time, simply because there are more people in the miss zone than in the strike zone in any given event. And the recalibration that says, "I went through that and came out okay," is the recalibration that produces the warning fatigue that reduces response rates to the next warning. The storm system that was already forming behind this one, the next pulse in a pattern that the atmosphere had been running all season, was going to arrive in the coming days with another warning polygon, another set of alert boxes on a map, another round of cell phone notifications and weather radio alarms, and television meteorologists interrupting programming to go live. And the 40 million people who had just been through this were going to have to decide, again, how seriously to take the next warning. The answer to that question is not written in the forecast models. It is not contained in the CAPE values or the wind shear calculations or the mesocyclone signatures appearing on radar screens in Norman, Oklahoma. It lives somewhere in the gap between what the atmosphere makes possible and what human beings decide to do with the information they are given. That gap has always existed. It existed before Doppler radar. It existed before the National Weather Service. It will exist after every technological improvement the next decade produces. The warning system can close that gap from one side. Preparation, awareness, local knowledge, and the decision to act before absolute certainty arrives can close it from the other. The storms do not wait for the gap to close. They arrive on the schedule the atmosphere sets, indifferent to whether the people in their path have done everything possible or nothing at all. 40 million people, one warning polygon, 800 miles of loaded atmosphere, and the storm was still only the visible part of a much larger story. The story of a country that has built itself into the path, that has watched the path shift eastward for 2 decades, that carries $17.8 trillion of reconstruction cost value inside the zone the atmosphere targets repeatedly, and that has not yet fully reckoned with what it means to live inside a corridor that the jet stream keeps finding, season after season, with the same ingredients, the same geography, and a warming Gulf of Mexico that makes the fuel richer every year than it was the year before. The next warning is already being written.